Hello everyone. So here we are at the beginning of the fourth week in this course. So in the last 3 weeks we learnt about the basics of rock engineering, and then we learnt about some of the various types of underground excavations, and then I mentioned to you that various ground conditions and how you can apply the stereographic projection in case of the analysis of underground excavations with reference to roof failure as well as the side wall failure. So, today we start another topic, that is elastic stress distribution around the circular tunnels. So, here we are going to derive the expression for the elastic stresses all around the circular tunnel, and also we will see some aspects related to the elastic displacements around the circular tunnels. So, to start with, let us first try to understand the geometry of the problem. So, since this is the first of this analysis, so we are starting with the most basic structure. That is, the first thing is we are considering the circular tunnel, and then when I come to the loading and the material properties, there you will realize that I am considering the rock mass or rock media as the elastic medium, which may not be true in the field, but to start with, that is at the first point of the analysis, it is always essential for us to first understand that how the system is going to behave in an elastic manner, and then maybe we can extend our discussion to elastoplastic analysis. So, as far as the geometry of the problem is concerned, see, we have a circular tunnel here. The axes are defined by the horizontal axis, which is the x axis, and a vertical axis, which is the y axis. This circular tunnel is excavated in a semi infinite rock medium, which is at a depth of h. See here, from the ground surface to the top of the circular tunnel, this is h. So, this is also called as overburden, and you need to keep that in mind that an assumption is involved here that this depth h is much larger than the radius of the circular tunnel, which is represented by a, that is small a. So, in all the directions, see, this is in this direction it is infinity, this direction infinity, this direction infinity. So, that is why we are saying that the tunnel is excavated in a semi infinite rock medium. Now, another aspect is that is the medium which is surrounding the tunnel, that we are considering to be infinite in both the reference directions, and any point that you take in this medium, which is represented by this circle, that can be identified as r comma theta. So, the coordinate system is going to be r comma theta, where r is the distance, radial distance from the center of the tunnel, and theta is measured in the anti-clockwise direction from the positive x axis. Now, this geometry is simulated in the theory of elasticity as a problem of stress distribution around a circular hole in an infinite plate of thickness T. So, basically we have the solution of such a problem in theory of elasticity. So, basically this problem corresponds to a problem of a long horizontal tunnel at depth in a uniform rock formation. Please understand that rock formation can never be uniform, but as a starting point, these are the assumptions which we are considering while going for the elastic analysis of the circular tunnel. Coming to the second aspect, after discussing the geometry of the problem, the second aspect is loading. Now, in this case, this medium is subjected to the applied stresses in x as well as y direction. So, in the x direction, this is Sx, and in the y direction, this loading is Sy, and these Sx and Sy, they are acting at the boundary of the medium. That means that they are far from the circular tunnel. And what is the boundary of the medium? That we consider to be semi-infinite medium. So, practically these stresses, they are acting at that large or infinite distance. So, again here this point is represented as r comma theta, and this is what is the stress system. So, please see here that what are we taking as the positive direction. So, if it is tensile in nature, that is what we are considering to be positive. So, if it is compressive, then we will have to put a negative sign in front of these applied stresses. So, this is what is all about the loading. As mentioned, Sx, Sy uniformly distributed along the thickness of the plate. Now, coming to the deformation or the displacement. So, in the radial direction, that is in r direction, you have the displacement which is represented by small u, and the displacement in tangential direction, which is perpendicular to u direction, is represented by v. Coming to the material properties, the material around the tunnel is assumed to be homogeneous, elastic and isotropic, and the engineering properties of such material is represented by modulus of elasticity and the Poisson's ratio, which is represented as E and mu here. Now, coming to the boundary conditions, which are extremely important here. So, at a distance which is quite away from the boundary, that means when r is tending to infinity. So, we have sigma r and tau r theta, which will be due to the stress which is applied at r tends to infinity. So, this sigma r and tau r theta can be expressed in such a manner that sigma r is equal to half Sx plus Sy plus half Sx minus Sy cos of 2 theta, and we have tau r theta as minus half Sx minus Sy into sine of 2 theta. So, I just combine these two equations and mark them as equation number 1. Now, another boundary condition will be at the tunnel periphery. So, once you excavate, so the tunnel periphery will become the stress free boundary. So, what will happen at r equal to a? You will not have any stresses. So, at this location, sigma r equal to a will be equal to 0, and tau r theta at r is equal to a will be equal to 0. So, I make this as equation number 2. So, these are the two boundary conditions here. Then the aim of this analysis is going to be determination of the stress distribution around the tunnel periphery in the surrounding medium. So, what we are going to get in this is the pattern of the distribution of stresses, that is radial stresses, tangential stresses, and then shear one, tau r theta along both radial r and the tangential directions. We are going to get the variation of sigma r, sigma theta and tau r theta along theta equal to 0 axis or you can call it as the x direction, and theta equal to 90 degree, that is y direction, and all around the tunnel periphery. So, since here we have seen that the geometry is symmetric, loading condition is symmetric, boundary conditions are also symmetric. So, that is why if I take 1/4 of the tunnel and if I vary the theta from 0 to 90 degree, I am going to get the symmetrical response in the other 3 quadrants. So, that is why here when I say that we are going to get the variation of stresses around the tunnel periphery. So, we are varying theta from 0 to 90 degree only rather than varying it from 0 to 360 degree. Then we have the variation of the displacements u and v at as well as around the tunnel periphery. So, this is what is going to be our aim of this elastic stress analysis. Now, how are we going to do this? So, we have the solution of such a problem in theory of elasticity, which involves the solution of the differential equation of equilibrium and differential equations of compatibility for a 2D situation. So, let us first try to see that what are the differential equations of equilibrium for a 2-dimensional situation. So, that is we can write as del x of sigma x plus del y of tau yx plus rho x is equal to 0. So, I make it equation 3 part 1. Then I have del x of tau xy plus del y of sigma y plus rho y to be equal to 0. This is 3 and part 2. So, these are the differential equations of equilibrium. Now, what happens to the differential equations of compatibility? How we can write it? So, that is del 2 del x2 plus del 2 del y2 of sigma x plus sigma y, that will be equal to 0. This is equation number 4. Now, these equations together with when subjected to the set of boundary conditions of the problem which we discussed just now. So, they give rise to the solution of this elastic stress distribution problem around the circular tunnel, and hence we will be able to obtain the stresses and then we can obtain the displacements. So, the approach to the solution that we are going to adopt is the Airy's stress function approach. So, we have the Airy's stress function which is denoted by phi, and if there is the absence of the body forces or the body forces are constant, then in that case the phi can be defined as sigma x equal to del 2 phi del y2, then sigma y is del 2 phi del x2, and tau xy is equal to minus del 2 phi del x del y. Okay. So, we had this equation 3 part 1. So, if you just substitute all the stress components in terms of the stress function phi, this is what that we are going to get. So, take a look here that del x of del 2 phi del y2 plus del y of minus del 2 phi del x del y. So, this is what that you are going to get is del 3 phi del x del y2, and then the second term will also be the same del 3 phi del x del y2. And you see that both the factors, both the terms, they are same. So, this is going to be equal to 0. Now, let us take a look at the other equilibrium equation, that is was given by equation 3 2. So, in that case what we have is del x of minus del 2 phi del x del y plus del y of del 2 phi del x2. So, if you just open these bracket and apply these operators. So, what you are going to get is minus del 3 phi del x2 del y plus del 3 phi del x2 del y, and this is also going to be equal to 0. So, therefore, what we can say that the stress function phi satisfies the equilibrium equations. Is it not? When we substitute on the left hand side of the equation with reference to the stress function, then we get automatically the right hand side of the equation. So, this shows that the stress function, it satisfies the equilibrium equation. Now, let us apply the same thing to the compatibility condition. So, compatibility condition was given by this equation number 4. So, let us try to write there del 2 del x2 plus del 2 del y2, and here it was sigma x plus sigma y. So, let us write it in terms of the stress function. So, this is what you are going to get, and that is equal to 0. So, what we have here is del 4 phi del x4 plus 2 times del 4 phi del x2 del y2 plus del 4 phi del y4, that is equal to 0. Please make this equation as equation number 5. So, any stress function phi, if it is satisfying the equilibrium condition, so it has to satisfy these equation 3 and 4 as well. So, the situation here we have that any stress function phi satisfying equation number 5 will also satisfy equations 3 and 4. So, to solve the problem of a circular hole in an infinite plate, we first assume a stress function of the form, say I take it like this, that is phi equal to a log r plus b r square plus c r square plus d r to the power 4 plus e r to the power minus 2 plus f into cos of 2 theta. So, this stress function phi is the function of r comma theta. That means it is representing any point in the medium, surrounding medium. And what about these a, b, c, d, e and f? So, these are a, b, c and so on f. These are arbitrary constants which can be obtained using the appropriate boundary condition of the problem which is under consideration. So, now in the polar coordinate system, the stress function phi is such that you have sigma r is equal to 1 upon r del phi del r plus 1 upon r square del 2 phi del theta 2. So, this is 7a. These are the basic equations in the theory of elasticity. Sigma theta is del 2 phi del r2, this is 7b, and tau r theta is 1 upon r square del phi del theta minus 1 upon r del 2 phi del r del theta. So, this is 7c. So, this is how we can write or represent phi in terms of the polar coordinate system. Earlier we were doing in terms of the Cartesian coordinate system x and y, but right now we are taking it with reference to the polar coordinate system, that is r theta. So, here what we have is say del phi del r is going to be, now you have the expression for phi in terms of r and theta. So, this is going to be a by r plus 2br plus 2cr plus 4dr cube minus 2e r to the power minus 3 into cos of 2 theta. Or you can write 1 upon r del phi del r is going to be a upon r square plus 2b plus 2c plus 4d r square minus 2e r to the power minus 4 cos of 2 theta. Make it equation number 8a. Then you can write del 2 phi del theta 2. So, this means that you have to differentiate the expression for phi twice with reference to theta. So, this is what that you are going to get, minus 4 cos 2 theta into c r square plus d r to the power 4 plus e r to the power minus 2 plus f. Or I can write 1 upon r square del 2 phi del theta 2, that is going to be minus 4 cos of 2 theta, and then we have c plus d r square plus e r to the power minus 4 plus f r to the power minus 2. And I will make this equation as equation number 8b. So, now let us proceed further. If I add these two equations, equation 8a and 8b, so what am I going to get? So, I write here as 8a plus 8b, and what am I going to get here in this form is that your sigma r, which was 1 upon r del phi del r plus 1 upon r square del 2 phi del theta 2. So this is going to be equal to sigma r will be equal to now a by r square plus 2b plus cos of 2 theta, and then here you have 2c plus 4d r square minus 2e r to the power minus 4, then minus 4c minus 4d r square minus 4e r to the power minus 4 minus 4f r to the power minus 2. So you see here this term and this term, they will get cancel out. So all you will get here is sigma r as a upon r square plus 2b plus, so this is 2c and minus 4c, so this will make it as minus 2c, and this is minus 2e r to the power minus 4, and this is minus 4e. So this is going to be equal to minus 6e r to the power minus 4, and remaining one will be this term, that is minus 4f r to the power minus 2, that is cos of 2 theta. Now make it equation number 9a. Now in the similar way we can have this sigma theta also. So sigma theta can be written as minus a upon r square plus 2b plus 2c plus 12d r square plus 6e r to the power minus 4 cos 2 theta. Make it equation number 9b. So this is how writing the stress function with reference to the r and theta, and finding out sigma r and sigma theta in terms of that expression. So that is what that we are going to get as equation number 9a and equation 9b. Now how to do it for tau r theta? So I have given you the basic expression for that. Just you need to submit all these expression to that basic expression. Let us see how we are going to get that. So what we have is tau r theta, that is going to be 1 upon r square minus 2 sine of 2 theta, and we have c r square plus d r to the power 4 plus e r to the power minus 2 plus f minus 1 upon r del r of minus 2 sine 2 theta into the same term, that is c r square plus d r to the power 4 plus e r to the power minus 2 plus f. Now this is going to be just further simplify. So if I take here minus 2 sine of 2 theta outside, so what I am going to get is c plus d r square plus e r to the power minus 4 plus f r to the power minus 2, and then this negative sign and this negative sign will make it a positive sign. So it will be 2 sine of 2 theta by r, that is so this I take outside. So what you have is 2 cr plus 4 d r cube minus 2 e r to the power minus 3. because here you have to differentiate it with reference to r. So, all these terms have to be differentiated. So, what we are going to get is that tau r theta is equal to sine of 2 theta, that is minus 2c minus 2d r square minus 2e r to the power minus 4 minus 2f r to the power minus 2. Now, we have taken sine 2 theta outside. So, 2 by r, that will be multiplied here. So, that will give me plus 2 by r. So, this is going to be 4c, then plus 8d r square, then 2 by r. So, minus 4e r to the power minus 4. This is what that we are going to get. Further, you just simplify this. So, you are going to get tau r theta as so let me first write this one. So, here you have 2c and 4c. So, this will become 2c. Then let us collect the terms of r square. So, here it is minus 2d and plus 6d, plus 8d. So, this is going to be plus 6d r square. Then let us collect the terms of r to the power minus 4. So, this is minus 2e and minus 4e. So, that will make it minus 6e r to the power minus 4, and this is going to be minus 2f r to the power minus 2 sine of 2 theta. Now, make this equation as equation number 9. C. Now, what we do is once we obtain this sigma r, sigma theta and tau r theta in terms of these constants, arbitrary constants a, b, c, d, e and f, now we need to apply the appropriate boundary conditions to determine these constants. So, let us take a look. So, we substitute the boundary conditions. So, first we take at say r tending to infinity. So, what we are going to get here is that half Sx plus Sy plus half Sx minus Sy cos of 2 theta, that is going to be equal to a upon r square plus 2b plus, so you have here minus 2c minus 6e r to the power minus 4 minus 4f r to the power minus 2 and cos of 2 theta. So, what we now do is we compare both the sides of the equation. So, comparing the terms on both sides of this equation. So, what we are going to get is something like this, that is half Sx plus Sy is going to be equal to a upon r square plus 2b, and of course, this is when r is tending to infinity, because we are substituting the boundary condition at r tending to infinity. And the other term is going to be half Sx minus Sy, that is going to be equal to minus 2c minus 6e r to the power minus 4 minus 4f r to the power minus 2. Of course, here also r tending to infinity. Now, what will happen? Focus on this expression. So, what will happen? Here r to the power minus 4 and here r to the power minus 2. So, when this r is very large or it tends to infinity, these two terms will become equal to 0. So, what ultimately that you are going to get is half Sx minus Sy is going to be minus 2c, and of course, in this case what you will get, see here, if this r is very large, so from here you will get half Sx plus Sy is equal to 2b. So, I will write this as equation 10a and this as equation 10b. Okay. Now, what will happen even at r tends to infinity to your tau r theta. So, what we are going to get is half Sx minus Sy into sine of 2 theta, that is equal to, we have 2c plus 6d r square minus 6e r to the power minus 4 minus 2f r to the power minus 2, this multiplied by sine of 2 theta. Now, again I compare the two terms and keep that in mind that this is also when r is tending to infinity. So, if I compare the terms, what I am going to get is half Sx minus Sy, and this is going to be equal to, now these four terms are there. When you have r to the power minus 4 or r to the power minus 2, what will happen when the r value is very large? These quantities will become equal to 0. So, ultimately what you have is 2c plus 6d r square. Of course, here since the term r is there, so I am just putting this caution here that this is subjected to r tending to infinity. Now, what will happen? Take a look here, that here is the positive power of r, and if this r is tending to infinity, what will happen to this term? This term itself will become infinity, or this will also tend to be very large as the value of r is increasing. So, what happens as far as the practical situation is concerned? You can never get the infinite stresses. So, what is the solution then? The only way that we can sort this out is if we say that okay, d is equal to 0. So, when this term, second term, that is 6d r square becomes equal to 0, then only this has some physical meaning, this equation has some physical meaning. So, what we have here is, as a consequence, this d has to be equal to 0 as no stress can be infinite. In any of the system, this cannot be there because it is practically not possible to withstand this. So, ultimately what we get is half Sx minus Sy, this is going to be equal to 2c. So, this I make as okay, I miss one negative sign. So, this is going to be minus half Sx minus Sy, that is going to be equal to 2c. So, we are going to write this equation as equation number 10c. So, you see that here we have applied as of now the boundary conditions at r tends to infinity, and we got three equations, that is 10a, 10b and 10c. And if you take a look, this equation 10c, which is half Sx minus Sy is equal to minus 2c, is it not the same as equation number 10b? Okay. So, ultimately here we have got only two equations, but one thing also we got, that the constant d will be equal to 0, so that the system has some practical meaning. So, we have few more boundary conditions which were at the stress free boundary, that is at r equal to a. So, we will continue this derivation in the next class with those boundary condition, and then I will tell you that how the expression for the stresses can be determined and how we can have the stress distribution all around the tunnel periphery. Thank you so much.